So the axis of the ring is the z-axis. The radius of the ring is equal to a, and we are asked to find the magnetic field each distance along the axis, each distance along the axis of the ring. So at any point, if we change this h in here, we can find the magnetic field at any point later on. So assume that we have a DC current I, and this is the radius here is A, which is fixed now. So we want to apply Biot-Savart in order to find the magnetic field at this point in here. Now, before we start, if you look into the physics, so if I want to measure the magnetic field at this point in here, where do you think the magnetic field is going to point, direction-wise?
Upward.
Omar?
Yes.
Yes. Why?
along AZ.
Why, Omar?
Because of the right hand rule,
Okay.
it will the A5 will cancel. We will are left with the AZ only upward.
So yeah. So if I take DL here, and I apply the right hand rule, the magnetic field is going to point along this direction. So it will have two components. One is a Z component and the rho component.
Yes, but we have the row will cancel each other
Why?
because of the symmetry.
Excellent, Omar. طيب, Omar, did you solve this one?
No, I looked at it and I tried to solve it.
Okay. Can you join so that we can solve it together, Omar? Can you join?
What do you mean by join?
Join with the webcam so that we can the class can see you.
Okay, but my connection is not that good.
It's okay. I'm just switch it on. It's all right. I'm going to help you, Omar, with this, so don't worry.
Okay.
So let's take it again. We want to explain to the rest of the class. So from where we start, Omar?
Should we find DL first?
So first we go to Biot-Savart. So Biot-Savart, this is for a line. We're not going to use the one that we did for the finite line. Finite line is not going to, it's not going to be applicable in here. Do you agree with this?
Yes.
The that we developed last class, it's not going to be applicable in here, is it? So this is why we have to start from the beginning, from Biot-Savart. Okay, so now select a representative from the current. So DL here with the direction of the current. So what do we do, Omar?
Is it A5?
Yeah, the direction is A5, but DL here is, again, it has a scalar part and a vectorial part.
The scalar would be rho.
Is it rho or A, Omar?
Here it's A.
Yeah, A, because A is constant. So
Yes.
can I say that DL here is going to be A d phi A phi? We just want to learn how to build the problem, how to build it slowly. And then we need R now. R, the usual definition, from the observation to the source, due to this DL. So we say that this point minus this point. So we need the vectorial now quantity. Again, it will have two components. One,
Yes, one along AZ and one along
arrow.
arrow.
And the arrow is negative because we take 0, 0 minus A. 0 minus A along arrow.
Minus A.
Yes, exactly. So we say that R minus A arrow, and then H minus 0, okay, H AZ. Okay, these are the two components of R. Can you see this, Omar?
Yes.
Right. Okay, now do cross product now between DL that we get in here, because we have a cross product. So do a cross product between this one and this one. So A phi cross with A rho.
It will be A squared.
No, cross product, unit vector. A row, A phi, sorry. A phi cross with A row. The cross product between unit vectors.
Minus AZ.
Minus AZ. And then A phi cross with AZ.
It will be A row.
A row, exactly. So the final here is A square, because I have A square. There is a minus sign from the cross product. So this is becomes AZ, and this is A row here. Huh? So this is now the cross product. So we take this now and put it inside the integral, and we need R cubed, because we used here R. So we divide by R cubed. Okay, so here we have this divided by R cubed. R cubed is what? It's A square plus
H square.
H square to the half, but we are going to raise it to 3 over 2, right? 3 over 2.
Yes.
And then the integral, we are integrating over 5. This is the integral of pi. So from 0 to 2 pi, so that we complete the whole ring. Okay? So this is how we set up the integral. You agree with this, Umar?
Yes.
Okay, how about the rest of the class? Do you agree with this? Do you agree with this?
Yes.
Okay, now
Makes sense.
Umar, let's continue now with what you concluded at the beginning, which is it was
A row will be cancelled. Will be
exactly. So we have a symmetry here, and this symmetry will cancel this row. Now we need to understand it slowly. Now, due to this DL, DH is going to be along this direction. It has these two components, which is this component and this component. But there will be another one as we integrate over phi. If I take the corresponding one from the other side there, okay, it's going to have a magnetic field along these directions. So the Z component will add up, and the rho component will cancel each other. And hence we say that by symmetry, this is going to go to 0. By symmetry, the second term here is going to go to, because I have two terms here. Huh? So by symmetry, I say that this is equal to 0. Now, if you don't notice this symmetry from the physics, remember that A rho is a function of phi. You cannot take it outside the integral. This A rho, as we did this twice before, is a function of phi. So you need to expand it in Cartesian coordinate system. So if I expand this in Cartesian coordinate system, A rho is equal to AX and AY, cosine and sine. Now, we are integrating now with respect to phi over one period. So this should be, mathematically, should be equal to 0. Okay, so here we say, from physics, we have a symmetry, we can cancel it directly. All right, if we don't notice this, mathematically, we cannot take A rho outside. We need to expand it into a Cartesian coordinate system. And hence it will cancel mathematically. So it's equal to 0. طيب, what is remaining now? Remaining is this. So what do you see from the rest of the integral now, Umar?
We have to integrate with respect to phi, which is 2 pi only.
Only 2 pi.
The
rest are constant. A is a constant. It could be 2 meters, for example. Huh? H could be 4 meters, huh? Something like this. Huh? So these are constants. So there is no variation with phi in this integral. So the integral will give us just a 2 pi. And then if we combine, so you have a 2 pi and 2 pi here, so you have just a 2 there. Now, so this is the magnetic field. It looks complicated, but as a matter of fact, it's only this cross product, and the rest should be straightforward. You agree with this? Did you get this result, Umar, in the analysis?
Yes, yes, I did.
Excellent. Thank you, Umar. Thank you very much. Excellent work. All right. Now you have now you can solve any other problem, huh? Whether with rings or other problems. But we are going to take this now and analyze it a little bit. Now this is valid for any point along the axis, huh? Along the axis. So if we change H here, we can find the magnetic field, for example, in the center here. So if I put H is equal to 0, then the magnetic field is going to be I over 2A, AZ. And the magnetic field is going to point upward along the Z directions. As a matter of fact, the strongest point in this expression when H is equal to 0, so which is in the center. So this is the magnetic field is going to add up from the whole ring. Now, if I put H negative here, this is for any H. So if it is positive, we know that it's going to be along Z directions. But how about it if it is negative? Since we have H square, so if you substitute, still the magnetic field is going to be pointing upward. And you can check this with the right-hand rule. So it's always along the axis, the direction of the magnetic field is going to be upward all the time. If we change the direction of the current, then it's going to reverse direction. Okay? So this is from this expression. But how about if I want to measure the magnetic field somewhere else, not along the axis? Then this expression is not valid because it's only valid for any point along the Z-axis. Because we killed the symmetry, remember? Huh? But if you go outside, you don't have a symmetry outside. So the rho component will be there. Then we have to start from the beginning. Now, in the book, you have this diagram here, just to show the direction of the magnetic field with respect to a ring conductor. So this is the ring conductor, and the direction of the magnetic field in the center is going to be upward. And then the magnetic field lines, they will close upon themselves. Huh? So this is here up, but here it is down outside. And this is always the case, no matter what the circuit configuration is, the lines of the magnetic field are going always to close upon themselves. Okay? This is always the case. So if you reverse the direction of the current, as we said, then this picture is going to reverse direction. Okay, so the magnetic field is going to be downward. Okay, any question with this example? Right. So this is the Biot-Savart. Now we go to Ampere circuit law, which is, as we discussed before, Biot-Savart is very similar to Coulomb's law. Now, Ampere circuit law is similar to Gauss law. This is Gauss law, but in a different form. Ampere circuit law says that if you do a circulation of the magnetic field around the closed path, this is going to be equal to the current inside. This is the current inside. And you write it mathematically as the circulation of H is equal to I enclosed. Again, this is a very powerful concept to solve symmetrical problems, as we are going to discuss with a few examples. Huh? Again, line as well as surface as well as volume. We are going to use it for volume, which is very powerful. But before we do this, if I have a circulation of a field, can I change it into a surface integral instead of the circulation? And in this case, we use the Stokes theorem. Huh? So if I use the Stokes theorem, I can change this circulation. This is the circle into the curl of H integrated over this surface area. And the current here, I can write it in terms of the current density, J. So the current density is, if I know the current density, then I integrate over the surface area. Now, obviously, if I compare between this integral and this integral, we get an equation which is the curl of H is equal to J. And this is the third Maxwell's equation. This is the third Maxwell's equation. So the third Maxwell's equation, which is the first in magnetostatic, it is coming from Ampere circuit law. It's the circulation of H is equal to I enclosed. This is written in integral form. And the equivalent of that is the curl of H is equal to J. And this is written in differential form because we have differentiations in here. Now, if I want to compare this to electrostatic, what is the equivalent of this expression in electrostatic? We did a Maxwell's equation, equivalent to this one in electrostatic. Ammar?
I don't remember it very clearly, but I think it was Q enclosed, and we used the Gauss, I think.
No, same expression, same concept. Replace H with E.
And give us Q, correct?
No, that was Gauss. That was Gauss.
I don't remember correctly.
Abdullah?
I believe it was we proved that the electric field is conservative because it's equal zero.
So what is the expression, Abdullah?
الكيرل حق ال E equals zero.
Exactly, yes. So the equivalent of this in electrostatic is the curl of E. This is the Maxwell's equation. Huh? The curl of E is equal to zero. Now, from physics point of view, the curl of E is equal to zero. It means that this is a conservative quantity. But in magnetostatic, the curl of H is not equal to zero. So we cannot say that magnetostatic field is a conservative quantity. So there are similarities between the two expressions, but their physics is a bit different. They're not the same. Okay, so this is the second Maxwell's equation. This is the third Maxwell's equation. Again, they are separate. This is electric and this is magnetic. And when we talked about this, we said that there is no magnetic field in the space. So we took only the electric part of it. And here also, we are saying that there is no magnetic field in the space. We are assuming that it's a zero. So two separate equations, but two separate concepts, but the equations are similar to each other. Now we are going to see how we apply this Ampere circuit law and why it is useful for our analysis, and will it complement Biot-Savart that we discussed before. So we'll see that if you look at the problem differently, you find that this is a useful relationship. Similar when we prove that Gauss' law is similar to Coulomb's law. It complements Coulomb's law. So we are going to do it now again. Let's take this example here, which we know its answer here. Assume that we have the z-axis is carrying a DC current, and this DC current is flowing along the positive z directions. Now, forget about Biot-Savart. We know the final answer from Biot-Savart. Now, if we ask ourselves now for this conductor, where do you think the magnetic field is going to point? How many components it has, and how to solve it in which coordinate system? And we are going to use, again, Ampere circuit law for that purpose. All what we know, that we have a DC current flowing in the z directions, and it's carrying a DC current I, positive z. Ammar?
Maybe cylindrical coordinate system, and
Okay.
the direction will be in phi direction.
According to the right-hand rule.
Yes, exactly.
Right? According to the right-hand rule.
Yes.
Then we say that from the physics of the problem, we say that H will have only one component, which is going to point in the phi directions. So this is our phi directions. Now, to set up the integral, we need a dl. So we know H. It has only a phi component as along a phi. Now we need a dl to integrate this one. Obviously, dl, if we take a path with the rho distance, this is a rho distance, and our dl is going to be in the phi directions. So I say that it's equal to rho d phi a phi. This is our dl. We are selecting this as an Amperian path. It's a hypothetical path that we need to integrate over, in which that we think that the magnetic field is going to be uniform over this path from the physics of the problem. So this is similar to a Gaussian surface that we selected in Gauss and the application of Gauss. So we say that if we select the dl as rho d phi a phi, and then we set up the integral in here, which is the left-hand side. According to Ampere circuit law, if you perform this integral, this must be equal to I enclosed by the Amperian path that we selected. So the Amperian path, what do we have? We have only this I, which is inside the Amperian path that we selected. So it's equal to, let's say if this is 10 ampere, we say that this is equal to 10 ampere. So the left-hand side of the integral is, we think that H will have only one component, and this is our selection of DL. And we integrate, again, it should be closed, so from 0 to 2 pi. A phi dot with A phi is 1. Now, do you think that the magnetic field is going to be uniform over this path if I keep the same row distance? And the answer should be yes, because if I keep the same distance in here, this H should be uniform. I can take it outside the integral. Okay, and this is why we have the symmetry. And then the integral will give us only 2 pi. So this integral will give us 2 pi. So we say that the integral will be 2 pi rho and multiplied by H phi. Now equate, this is the left-hand side of Ampere circuit law, equate to the current inside this Amperian path that we selected, which is equal to I. So this is equal to I. And then from that, you calculate H. So H should be equal to I over 2 pi rho A phi. Remember that we did this from Biot-Savart last time. We said that if you have an infinite thin conductor carrying a DC current, then the magnetic field is going to be in the phi directions, and this is the how to calculate the magnetic field. So it means that this Ampere circuit law complements Biot-Savart, but we are looking at the problem from a different angle. Okay, now we are going to take it into more involved problems. Yes, Nawaf, تفضل.
Doctor, in the last step, we have H, we can find H as a magnitude, and then we multiply it by I phi to get the vector, or because it is from the beginning, we know it is along A phi.
When we started solving the problem, this is what you mean? When we started the problem?
Yes.
Yeah, when we started the problem, we think that we don't know about Biot-Savart. Huh? Forget about Biot-Savart at the moment. Huh? So we want to implement this circulation of H. So we look into the physics of the problem, okay? And we say that according to the right-hand rule, the magnetic field will be in the phi directions because the current is along Z. All right, it's going to have only one component, which is phi component. And then from that, we selected a path in order to perform the integrations. This path, again, is going to be along the phi directions and should be closed at any arbitrary row. Any arbitrary row, doesn't matter. Okay, did I answer your question, Nawaf?
Yes.
Okay, good. Now, I need you to concentrate in the following now. This is a solved example in the book. You will find that the final solution is very straightforward. It's not, but we need to explain the physics a little bit. It's not difficult. Assume the following. This is the first time we see surface current density. This is called the surface current density. It is ampere per meter. What does it mean? It means if you have a sheet here, so which is the XY plane in our case. Imagine that we have current flowing in the surface, current, and we represent this as the total current per unit width. It's ampere per meter. Okay? So imagine that it says here, imagine that the XY plane is carrying, the whole XY plane is carrying a uniform current density along the Y directions. So this is uniform, huh? KY here is uniform. Let's say it's equal to 20 ampere per meter. Okay, so this is, we get this in applications. Huh? You have a surface in which that you have a conductor as a surface, and then you have current flowing inside this surface. Now, we want to find the magnetic field everywhere. Everywhere, it means that any point above the sheet or any point below the sheet. And obviously that we have a symmetry here, and we want to look for this symmetry in order to understand how to solve this problem. Okay, so let's apply this Ampere circuit law. The circulation of H is equal to I enclosed. In order to explain this, I'm going to take this Amperian path around the sheet. And I want you to imagine this path. It's half of it is above the sheet and half of it is below the sheet. This dashed area here, this dashed line is below the sheet. So the path is closed, first of all. It should be closed. So we are going to integrate from 1 to 2, from 2 to 3, 3 to 4, and then 4 to 1. Okay, so we need to integrate along this line in here. Now the width of this line is B and the height is A. Okay, so again, these are arbitrary. It could be any number, it doesn't matter. And then we need to calculate how much current is passing through this line. Since I have a current density and it's equal to Ky, so the current enclosed is what? It's going to be Ky multiplied by the width. So it's going to be Ky multiplied by the width, which is equal to B. So this is the current on the right-hand side. But let's solve the left-hand side of the integral. Let's see how to perform this for the left-hand side of the integral. Now, first of all, we need to find the symmetry of the magnetic field. I'm going to rotate the sheet such that we look at the sheet from the y-axis, like this. Okay, so the current density is coming toward us now. Okay, so we're looking at from this angle here, along here. So the current density is coming toward us. So this is the z-axis, and this is the y, and this is the x. Okay, and the sheet is the current density is here. Now, from this current density, this sheet, let's assume that the current density consists of infinite lines of infinite dimensions, and they are flowing along the y directions. So imagine that I have a conductor here, infinite in size, parallel to the y-axis, and it's carrying a current uniform along the positive y directions. And next to that, you have another one. So the whole sheet consists of infinite lines. Okay. Now, at the moment, let's just take two lines. This is an infinite line and another infinite line. And we call them 1 and 2. Only 1 and 2. And let's take any arbitrary distance above the sheet. Let's say we are measuring at H in here. And then later on, we are going to measure at same point below, at minus H. Okay. Now, forget about the rest of the lines. Let's just concentrate on 1 and 2. Now, if I want to find the magnetic field due to this line here, alone at this observation point, above the sheet H, then if you apply the right-hand rule, you'll find that the magnetic field due to this one here is going to point along this directions at this point. And if you apply the magnetic field due to this, the number 2 here, the magnetic field is going to point down. This is DH2 and this is DH1. And then since they are exactly the same, then do you think that the Z component is going to cancel, and hence the magnetic field is going to point only along the X directions, here. It's only along the X direction. So the Z component will cancel, as you can see. Now, if I repeat for a point below, for this line is going to point along these directions, and for this line is going to point along these directions. Then can I say that the magnetic field is going to point along negative X direction? This is X direction, this is negative. All right? Now, these are only for 2 lines. Now, if I bring the other lines, you remember that the sheet consists of infinite lines next to each other. Now, if I bring the other lines, so if I take any point above the sheet, and since this is infinite, so where do you think the magnetic field is going to point if I take a point above the sheet? how many components it has? How many components is going to have? If I take any
Still
point,
one. Still
which is along the x directions. It's always, if you repeat this again to the left, it's going always to be along the x direction. How about below the sheet?
Negative x.
Obviously, it's going to be a negative x. Then we can conclude from this analysis that if you take a point above the sheet, it's going to be h0. We don't know h0. We are going to calculate it. But its direction is going to be ax. And below is going to be the same picture, but minus ax. Okay? Now, let's go back to the circulation now. We are going to do the circulation. Now, the circulation, I'm going to put it here so that you can see it from cross-section. So this is 1, 2, 3, 4, and then 1. So this is our path. And remember that this is equal to B. This is equal to B, and this is equal to A. Now, if we do circulation, we know that above is going to be AX, and I multiply by B. So this is H0 multiplied by B, which is from here to here. But when we integrate from here to here, the magnetic field has no directions along the Z directions. So this is going to be equal to 0. And when we integrate from here to here, this is along negative X direction. So the integration will be minus B multiplied by minus H0. And from here to here is going to be equal to 0. So we can say that the circulation, which is the 4 integrals, 2 of them are going to be zeros. This is 0 and this is 0. From the physics, because we said that there is the magnetic field is going to be along X direction. Then the 2 integrals that will survive is this integral with a minus B and this integral with a plus B. So this is plus B and minus B. And hence, if you add them all, you'll find that it's equal to 2H0 times B. So this is the left-hand side of this integral. And this must be equal to the current inside. How much current we have inside? Current I, remember, in ampere. But this is given as ampere per meter, which is current density per unit width. So if I multiply by B, this is our B here. Okay, so the current density, the right-hand side is going to be equal to Ky multiplied by B. And then from that, we can solve for H0. So H0 is going to be equal to Ky, the current density, magnitude, divided by 2. So now we found H0 here. So substitute in our expression here that H in general for a point of the sheet is going to be the current density divided by 2, and its direction is X. And below the sheet, it is exactly the same, and it's going to point along minus AX. Now, you notice that there is no dimension involved in the final expression. And this is due to the infinite nature of the sheet. The sheet is infinite along the XY direction. This is if the sheet is in the XY plane. Can we develop a relationship when the sheet is not in the XY plane? Similar to what we did in the infinite surface charge density, if you remember, in the electrostatic. And the answer is yes. We can say that if you have the sheet anywhere now, so you have a half, first of all, the current density, the whole current density, K, crossed with a unit vector normal to the sheet to the observation point. What do we mean by this? This is a unit vector normal to the sheet to the observation point. For example, in our case in here, if we are measuring a point above the sheet in our case, so AN here is going to be AZ. So if I'm measuring here, for example, it's going to be AZ. So let's apply it. This is AY. It is AY. Cross with AZ. This will give us AX. So above the sheet. But if I am below the sheet, AN is going to be minus AZ. So AY crossed with minus AZ is going to give us the minus AX. So this will work if you put the sheet anywhere now. All what you need is a unit vector normal to the sheet to the observation point. Okay, do you have a question in here before we solve an example? Right, let's try to understand this from a next example, which is example 10. I want to give you time to think about this one. Let me explain it, and I need your answer in a private chat. It says in here, we have, this is the X and the Y is inside, and this is the Z axis. We have two sheets. One is sitting at X is equal to 5, okay? And it is parallel to the YZ plane. And another one is sitting at X is equal to -5 and it's parallel to the YZ plane. And we're looking at the cross section here, okay? Now, this sheet is carrying -10 AY. So the current density here is flowing negative Y direction. While this one in here is carrying a current in the positive Y direction. So they are opposite to each other, two sheets. So think of this, this is the YZ plane, and assume that you have two sheets of paper, okay? And these are carrying current inside them. And they are parallel to the YZ plane. Now, we want to find the magnetic field in the everywhere, meaning that we are going to divide this into regions now. And we say that, for example, in this region, when X is greater than 5, we find the magnetic field due to the combinations of the two. And when it is between 5 and -5, we find the magnetic field in between. And when it is less than -5, we find it in here. Okay, so let me give you a few minutes, and then I need your answer. Okay, you know what to do, and the expression that we just developed is half K crossed with a unit vector normal to the sheet. So tell me what we should do. I just want to take attendance random name again, please. So if your name comes, please just switch on your webcam. Badr Ibrahim. Badr?
Yes, sir.
Just your webcam, please. Thank you, Badr. Kumail Abdulaziz Al-Qadi.
Yes, doctor.
Yeah, your webcam, please. Thank you, Kumail.
Can you see?
Yes, yeah. Thank you. Muhammad Adil.
Yes, doctor. My laptop is off, doctor, so I joined from my PC.
Next time we need the webcam, Muhammad.
Okay, sure.
Please. So I'm going just to put a note here. For next time, if your name comes, please just get ready with the webcam. Okay, we have an answer. Okay. In the middle, How about outside, Saud?
I think 0.
In the chat, Saud, in the chat, please. Okay. Fine. Some people, they just answered with a number. We have 3 different regions. So you need to say that in this region is equal to this, in this region is equal to this, and in this region is equal to this. So the 3 different regions in the same chart. You can say, I mean, in this region is 0, and then, but we need the others as well. Excellent. I think most. Okay. Type. Okay. Okay, so we stop in here. We stop in here. Everywhere is 0. طيب سعود, please. سعود.
Yes, doctor.
Yeah. Okay, let's try to solve it, Saud. You have a webcam, Saud, so that we can solve it together?
Yes, of course.
So tell us what to do, Saud, now.
Is it working?
Let's take it one at a time.
Yes, doctor. Wait.
Okay, Saud, we're waiting.
Yeah, doctor, I have a problem with the camera. Wait.
Okay, so. Okay, because of the time now of the lecture, so tell us, let's call this one sheet 1 and sheet 2. So what to do? So if we start in this region to start with, so.
Yes, doctor, yes. We first use the formula.
Okay. So we're talking about this region here now, This region.
Yes, k is greater than 5. X greater than 5. We will get AY cross AX.
Okay.
Along the magnetic field, and it will be 0 from the cross.
Which one is going to be 0? Now, how to solve for both of them? Are you solving for this one or this one?
Yes, first at the right side, minus 10 over 2k AY cross AX.
Are you solving for this sheet or this sheet? So
no, no, on the left side. Sorry.
We're talking x greater than 5. So we're measuring here. Remember, we're measuring at this point, for example.
Okay, we take 10 over 2.
Okay.
AY cross AX minus 10 AY cross AX.
So are you doing superposition, you mean? Are you
Yes.
doing superposition, H1 and H2? Okay. Now you say that for H1, what would be AN in this case? So assuming that I'm measuring only for H1, what would be here AN?
It will be AX.
AX. So AX cross, we have AY. This is A minus AY. Minus AY. Cross with AX will give us what?
Minus AZ.
AZ with a minus sign. There is a minus sign.
Yes, minus
AY cross with AX is minus AZ. There is a minus sign. It's going to be AZ.
Yes.
For the second one,
For the second
one, AN is the same, which is AX. Right?
cross with the minus
Okay.
minus AX cross with the AY.
The second one is AY. AY, you will cross it with AX. So this is a minus AZ. And the previous one was positive AZ. So the first one in here, this is the first one here for this one, minus AY cross with AX. So AY cross with AX is minus AZ, and there is a minus sign, so it's a AZ. This one is AY cross with AX is a minus AZ. So the total is 0. But in between
it will be
for this sheet, AN is what for this sheet, for the first one? Is it? Normal along the observation. So it's a minus AX. Huh? For this one is minus AX.
minus AX with AY with minus AX, it will be AZ. Minus AZ.
We have two minuses, first of all. There is a minus here, and AN is a minus. Okay, so it's a plus. So it's AY cross with AX now. It's a minus
AZ.
Yes. And for this one, AN now is AX. So it's AY cross with AX. So this is a minus AZ. So both of them is minus. So we say that for the first one is minus AX, so it will give us minus 5 AZ. And for the second one is AX, and this will give us again another minus 5 AZ. And the last one, it means that the summation is going to add up in here. Huh? And the last one is a repeat of this one. But AN now is negative. Huh? If I measure here, AN for both of them is minus AX. And this is also minus AX. So both of them will give us minus AX. So this is H is going to be 0. Meaning that the total now, if we look into this, the physics of this, the total is going to be 0 outside, and it will add up inside. Okay,
like
so it will add up.
Electric field measure between
Magnetic field.
It's like the electric field when we measure.
Exactly. Just like the parallel plate capacitor. Yes, when we add the positive and negative, the charge is equal, exactly equal. In between, it add up, and outside it cancels each other.
Yes.
Okay. But any question with this problem? Do you have a question with this problem? Thank you, Saud. But next time, please, your camera, Saud. Yeah?
Okay.
Any question with this one? Now, this is Ampere circuit law. We did now for a line, and this is for a surface. Now, this is an example in the book. Let me explain the example and what I want you to do. It's a bit lengthy example, but it's very important for applications. You remember the coaxial cable. It says here we have two conductors, an inner conductor with a radius A and an outer conductor with a thickness of between B and C. The thickness of the conductor is between B and C. The inner conductor carrying a DC current flowing along these directions. Now, when you connect the coaxial cable, you connect it to, let's say, a load, your TV, for example. Then the return current will come back on the outer conductor, the same amount of current, and it is uniformly distributed over the surface of the conductor. Now, if we put this in the XY plane, okay, this is how it looks, cross section of this. So this is the inner conductor carrying a DC current along Z directions. And the same amount of current, the return current, is flowing in the thickness of the outer conductor between B and C. Okay, and again, the current assume it to be uniformly distributed over the surface of the conductor. Now, the question here says that find the magnetic field everywhere. Everywhere, it means that we have 4 regions. Inside here, if I want to measure the magnetic field here, this is the first region. In between A and B, and inside the outer conductor between B and C, and outside. How much is going to be the magnetic field in all these 4 regions? So how much is going to be outside? Do you think that, what would be the magnetic field outside? Any idea?
0.
It should be equal to 0. Again, you have the solution please understand it. We are going to start the class next time with this one with questions to you so that you understand the mechanism. This is a very important example. So I'll see you inshallah on Sunday.